So last time, I think we briefly mentioned the isotherms for real gas. And we know that if the temperature is higher than some critical value, for instance, in this case, there's a critical temperature labeled as TCR. If the temperature is higher than this, then the isotherm will behave similarly to a ideal gas. Right? As you go higher and higher in terms of the temperature, P times V will be close to a constant, which means that it's closer to an ideal gas. However, if your temperature is going down, for instance, reaching to a temperature that is lower than this, then you start to see the deviation, and you start to see an inflection point over here, right? And last time we mentioned that for this inflection point, you have, because this is a pressure as a function of molar volume or volume. Therefore, at this point, you have the slope being 0. So partial P, partial V will be 0. And at the same time, since this is an inflection point, the second derivative will also be 0. Therefore, on the right-hand side, the curvature is downward, but the left-hand side, the curvature is upward. And if you further go lower temperature, the behavior of the isotherm will be stranger because when the volume is bigger than this, let's say a critical volume, the behavior is close to gas. But if you keep decreasing the volume, when it reaches this point, it will just go through a straight line. There's a horizontal line that you'll go through. And then the P as a function of volume will go up again. And during this transition time, this transition period, actually it's a coexistence of vapor and liquid phase. So this is a condensation process. So when you go from this end to this end, you're actually having this phase transformation from gaseous phase, from vapor to liquid. So basically, this is a condensation process, and from this end to this end, you have more and more liquid. And when you reach this point, the whole, let's say, the gas molecules will be condensated into liquid. And then when you keep shrinking the size or the volume of this container, the pressure will be increasing again. And you can see that the slope over here is sharper than over here. Right? If you look at the vapor side and the liquid side, you'll see that the slope is very different. And the reason for that is because for liquid, you need a huge pressure in order to change your volume by a little bit. Right? Like if you're over here, you only need to change the pressure, this axis pressure by a little bit to change the volume. However, if you're on this end, you have to increase the pressure by a lot in order to change the volume by a little bit. So please note that when you have these two phases, on the right-hand side, for the vapor phase, the slope is not that sharp. But over here, the slope is much bigger because you need large pressure to compress your molecules. So this is a condensation process. Later, we'll see that why this is considered as a flat line. If we start from the real gas, let's say like a van der Waals gas that we will see later, if we start from the state equation, the PV the pressure is a function of volume. If you solve that, it's actually not a straight line over here. It's having some sort of maximum and minimum. But there are some regions that are not physical. So a better construction is that the PV line will just follow a straight line, a horizontal line, and make sure that the Gibbs free energy from the liquid side and the vapor sides are the same. So basically, you'll go through this straight line, and then this is the condensation process. Okay, so last time we also mentioned that this is, these two derivatives will be 0. And later we'll use these two to solve some quantities. Actually, we've already mentioned this last time. And this is what I just talked about, the large value of partial P, partial V at a fixed temperature, because remember, each line represents an isotherm, so that's constant temperature. So this large slope in the ranges of liquid states and the small value of this in the ranges of vapor states indicates that the low compressibility of liquid and the high compressibility of the vapor phase. So this is what I just mentioned earlier. And when the temperatures increase towards this T critical, the vapor in equilibrium with the liquid becomes more dense, and the liquid in equilibrium with the vapor becomes less dense, which means that the boundary which defines liquid and vapor is becoming more and more vague. And therefore, when you reach the critical temperature, there's no distinguishment between the liquid and the vapor. Okay, so those two phases, they coexist with each other. So when the temperature is reaching this critical value, typically you only have just one phase. Okay, you just have one phase. So this is what I just mentioned last time. The temperature is above or below the critical temperature, you have this distinguish between the liquid and the vapor phase. And if you go beyond that point, go beyond the critical point, then the liquid and the vapor, they are all the same, so we'll call this supercritical fluid. So there's no distinguishment between the distinguishment between the liquid and the vapor. So on the textbook, you'll see this graph that below the critical temperature, you have vapor, liquid, as they are separated, and in between them, you have this vapor and liquid phase, which can coexist, right? If you go from here to here, then you'll see that your phase will transform from vapor to vapor plus liquid, and then it will become a pure liquid form. However, if you are starting from this point, like state 1, and you change the, for instance, the cooling of the gas at constant P. So the pressure is a constant, but you change the temperature. Also note that this, when you change the temperature at a fixed pressure, you are not, you are actually changing the molar volume, volume as well. So you'll move from this state to this state. Remember, the real phase diagram, actually we'll see later, is having 3 axes. So this is P and V, but in fact we also have a temperature axis. So remember that for last chapter, for chapter 7, we're mainly talking about the P versus T phase diagram. So you have something like this, right? If you still remember. If you project the this 3-dimensional phase diagram onto this PT plane, you'll see this phase separation, solid, liquid, gas. But on the other hand, if you're projecting those phase diagrams onto the PV plot, you'll be seeing the thing that we saw just now, that you have, for instance, this is vapor, let's say gas, and this is liquid, and this is liquid plus gas. Something like this. Later we'll see a construction of the 3-dimensional case. And basically you project the morphology of that phase diagram onto PV plane or PT plane, you'll see these kind of phase boundaries. And here we're talking about changing the temperature. So basically, we're say, so here we have, let's say, gas, and here we have liquid. But if you move from here to here on the PV plot, it essentially means that you're moving out of the blackboard plane. You're moving along this t-axis. So in reality, we're actually moving along this surface. It's hard to explain, but you're starting from this point around here, and then you're moving with a constant pressure. So pressure is a constant, but you're increasing the temperature. So you're moving along this surface from here to here. Okay, so that's the projection onto this PV plane. Then you'll see sort of like a horizontal motion, like from the right-hand side to the left-hand side. But actually, you're just moving on this surface, from this point perhaps to this point. And know that you're starting from a supercritical fluid region. Okay, you're starting from a supercritical fluid region. So there's no distinguish between this supercritical fluid and this liquid. So there's no obvious phase transition. There's just this continuous change in terms of the density of your, for instance, gas molecules, or you can say liquid molecules. So consider it as a fluid. So whenever you're moving, for instance, if you're starting from this point, you increase the temperature to beyond this yellow line. And then you move up by increasing the pressure. And then you further cool it down. So basically, you're moving from this up to here and then come back here. Then you'll only see a continuous change of density of your fluid. There's no condensation that will happen. However, if you're moving from, for instance, this point, just by reducing the volume or increasing the pressure at a constant temperature, then you'll just move from here to here, and then you'll go through this flat area, which means that you're going through a condensation process, therefore a phase transition, and then go back up again. So if you have this 3D image in mind, then you'll realize that if you go from here to here and then back to here, there's no so-called phase transition. There's only this continuous change of density. So under a new version of textbook, you'll see this PT plot like this, I think. So if you have PT plot like this, right? So you have the liquid, solid phase, liquid phase, and gas. But actually, here is the, for instance, the critical point. And you'll see boundaries like this. So basically, if you start from this point, and if you go from here to here, this will be similar to what I just mentioned. If you start from this point, you go up, and then you go back to the liquid phase, right? So you go from here to here. Then there's no change in terms of crossing this boundary, so there's no phase transition. However, if you're going from here to here, for instance, 1, 2, 3, 4, then you have to go through the condensation. So there's this coexistence of gas phase and liquid phase when you go through that green region, which is called the condensation region. And bear in mind that the plot we see over here is a projection of this onto the PT plane. And on the other hand, the plot we saw earlier for the isotherms, those are the projection of this like three-dimensional surface onto the PV plane. You see this. So this is another example which includes here we only have liquid and gas. But if you include solid as well, you'll see that here we have a solid and liquid, let's say the phase boundary. So this 3 lines corresponds to the lines that we just mentioned over here. Okay, we have the boundary of solid and liquid to gas. Okay. And again, here we have the critical temperature, and this is the critical point. So when you project these onto the PT plane, it will be this point over there. Therefore, if you're dealing with ideal gas, if you're dealing with an ideal gas without any phase transition, this is the three-dimensional PVT surface that you'll see. Okay, you'll just see a lot of isotherms, and these isotherms, they will if they combine with each other, it will become a continuous surface. And when you increase the temperature, of course, this isotherms they will move up, right? They will move up to a higher value. So you'll see this kind of gradient. But in reality, when you're dealing with real materials, for instance, if you're dealing with real gas, this is what you will typically see, like we just saw earlier in the previous slide. And this is for a substance that contracts upon freezing. So which means that you're dealing with regular materials like carbon dioxide, or some regular materials. If you're dealing with water, again, we know that for water, this slope, this one is negative, right? So the slope of that line will be different from the regular material because the substance will expand upon freezing. Therefore, this line over here will have a negative slope. So other things are similar. You still have this condensation region, except that this line is having a negative slope. Okay, so please bear in mind that this is when you're dealing with the phase diagram on the PT plot or on PV plot, you're actually projecting these surfaces onto each plane. Okay. So this is like I just mentioned earlier. If you have a surface like this, this is a regular material, okay? So for instance, carbon dioxide. If you project all these onto the PV plane, you'll see this kind of phase separation. So this C point is, again, the critical point. And previously, in this textbook, in this chapter, we only see the gas and liquid phase separation. So we're only seeing this part, let's say B, C, and D, okay, this part. But if you include the solid part, you'll start to see this region over here, okay, this region over here. So if you still remember that, if you learn from the first year of material science, introduction of material science, you see this kind of phase diagram, right? So it's similar that you have, for instance, this is alpha plus beta phase, and you have the, what is this? Liquid plus alpha and liquid plus beta, something like this. So this is a similar phase diagram that you'll see later in next semester. So those are for the concept of PV plot and the isotherms for real gas. And now we start to switch gear to the equation of state for real gas. So again, we will start from ideal gas. And we know that for ideal gas, it will obey the ideal gas law. Therefore, PV over RT should be close to 1. Right? If it's 1 mole of ideal gas, this factor, PV over RT, should be close to 1. So therefore, Z equals to 1 for perfect gas, or the perfectly ideal gas. But in reality, this factor, PV over RT, is typically a function of pressure and temperature. So, which means that for real gas, if you measure PV over RT, this number will not be 1. This number will be 1 only when the pressure is low, and only when the temperature is high. And So typically, you'll see this kind of plot that you use Z as a function of pressure. You'll see that when the pressure is extremely low, so close to 0 atm, this number is close to 1. Which means that when the pressure is low, the behavior of a real gas will be similar to an ideal gas. And if you increase the pressure, you'll start to see this linear change. So the slope is negative. For instance, for let's say for nitrogen, you start to see this decrease, and then you have this increase of slope to go up. So if you're dealing with, say, for instance, pressure that is less than, say, 5 atm or 10 atm, then you know that the slope of this one, if you plot Z as a function of pressure, it will have a negative slope. And when you increase the pressure to some critical value, this behavior will start to return to positive slope, and then it will just go back up. And the only exception is hydrogen. If you look at hydrogen, you'll see that the slope is always positive. Okay, the slope is always positive. So there are several ways to describe this behavior. And to model that, we'll just say Z, this PV over RT, this ratio is a linear function of P up to 10 atm. So let us just focus on the low pressure regime first. And we know that this Z, PV over RT, can be expressed as 1 plus MP. Okay? So to simplify it, so this is pressure, and this is Z. And Z is PV over RT. And typically, we'll start from 1. We start to see this kind of behavior. So this is Z equals to 1. And typically, this is, if you look at the previous real data, this is less than 100 atm. So let's say this is, say, 50. So when the pressure is much less than 50 atmospheric pressure, you can say this is a linear trend with a negative slope. Right? So let's say it is having this behavior. So Z as a function of pressure is 1 plus, let's say, MP. And this M is the slope of this plot. Because we know that when the pressure is 0, Z is close to 1. So if you have this expression, then you can rewrite the gas law, right? Because we know that now PV over RT is not 1, it's a function of pressure. So if you move the terms around, it turns out that you'll have this expression like this. Or you can say P times V minus MRT equals to RT. So from the real data, we know that M is negative. So this slope is less than 0. Therefore, this whole term is positive, right? Including this minus sign. So it is similar to V plus something, right? V plus a positive number, or V minus a negative number. Because we know that the gas constant and temperature, they are both positive. Okay. And this volume, this effective volume, is also a function of temperature. So this B prime over here will be the product of M times R times T. It should have the dimension of volume, right? Because it's right next to the volume term over here. And it is temperature dependent. So when you increase the temperature, you're actually changing this effective volume. And the deviation from ideal gas behavior can be dealt with by taking a correction to the volume term. So this is our first guess. of what the real gas equation should be. So we can guess that it should be something like this. You have some volume correction. So once you have this volume correction, maybe you can, let's say, simulate or predict the gas behavior more accurately. And that's based on the experimental evidence that we measured from real gas. And if you look at ideal gas, if you still remember the assumption, it is based on the assumption that those gas molecules are non-interacting. They are not interacting with each other. And more importantly, those particles are volumeless. So we treat those particles as just point particles. So they are not having a certain volume. But in reality, we know that those particles should have a finite volume. And they will interact with each other because there's a possibility that those particles will hit each other, right? So there's a possibility of collision of those particles. So therefore, for real gas, the volume is small, but nevertheless finite. So therefore, they have a finite volume. They have a finite volume. And therefore, for real gas, the volume available to the movement of this large number, Avogadro numbers of particles, should be less than the molar volume of the gas by an amount equal to the volume excluded by the particles themselves. What does that mean? It means that if you're dealing with ideal gas, originally you have volume like this. So let's say this is the ideal gas volume. And you have particles in it. They're moving around, and they don't have volume for themselves. So this V ideal is the same as the volume of the box. However, if you're dealing with a non-ideal gas, we know that these gas molecules, so these are much exaggerated, that you have volumes for your particles. So the real gas volume, let's say real, should be V minus some certain value, right? Because you have to exclude the volume for the particles. So it must be something that is smaller than the ideal gas volume. Some volume has to be excluded because these particles, they have finite volumes. So the real space that the particles can go to are these shaded areas, right? So let's say this is less than the total volume by the volume of the particles. So only when you can exclude that, you can know like how large the space those particles can go. Therefore, this sentence is important, that to the volume excluded by the particles themselves. So you have the original volume for the container, but you have to take the particles out because those are having some finite volumes. So also note that with the exception of hydrogen, B prime is a negative quantity over a narrow range of low pressures. So this will go back to this experimental data shown over here, that only hydrogen, the slope is always positive. So let's say hydrogen, for hydrogen, this B prime will be positive. Right? Because for B prime, for hydrogen, this slope is positive. So therefore, for hydrogen, this m is greater than 0. So this is a positive number. For the rest, m is less than 0. So this will be a negative number. So it's kind of odd, right, that the volume can be positive or negative. Typically, when you say, based on the things that we just mentioned, this volume should be always positive, right? Because you're excluding a positive volume. So if you're using this picture, then it seems that only hydrogen can be fit into this picture. But in reality, there are also other factors that will affect this kind of slope. It's not only the exclusion of volume, but also the interaction of the interaction between the gas molecules, which will change the pressure term. Okay? So of course, over here, if you just use this naive model, it seems that only the hydrogen can work, can fit into this picture. Okay? But in reality, actually, we'll see that for van der Waals gas model, this number B is always positive. It's always positive. But of course, over here, if you use other gases, then B prime will be negative number, right? Which seems to be weird. But this is only the first model that we see. Later, we'll see a more complicated model. More interestingly, like if you try to plot this, let's say PV over RT as a function of reduced pressure, and if you use the reduced temperature to gather them, the data for different gases onto the same line, you see this kind of universal behavior. So, like I mentioned earlier, this line is a function of pressure, but this is also a function of temperature. So here we plot Z as a function of pressure, but in fact this is also a function of temperature. So let's say this is the temperature for temperature T1. For higher temperatures, you can see that the line will move up. So you can imagine that over here, if you increase the pressure, increase the temperature, this function of Z as a function of pressure will move up, right? And more importantly, if you plot these as a function of reduced pressure, which is P over P critical, then for different kinds of gas, all those data will collide onto the same line. So for each temperature, let us look at, for instance, TR, which means that T over T critical is 1.5. And you'll see that for nitrogen, methane, water, for all these different kinds of gas molecules, they can be plotted onto the same line. So it means that there must be some universal behavior among these gases. And if we can figure out what the P critical and T criticals are, for different kinds of gases, then we can describe their behavior using the same equation or the same gas state equation. So all gases obey the same equation of state when expressed in terms of the reduced variables. And reduced variables means that you're using P over P critical and T over T critical and V over V critical. So remember that we just saw that P critical, T critical, and these are the things that we just saw earlier. If you still remember, if we go back to this line at the very beginning. So over here, we have the T critical, which is this isotherm. When you are having this temperature, you have the T critical, and the point at which the inflection point is will be P critical and V critical. So as long as you know these three values for a specific gas, and if you plot this function Z in units of reduced pressure instead of the real pressure, then you'll see all kinds of gases, they all behave the same. Which means that if you take out the material dependent factor, which is related to these three things, then the behavior of all gases should be similar to each other. So this is similar to what we learned earlier, I think in chapter 5 or 6, that for the Debye model, if you still remember, for different gases, for different solids, if you have T versus CV, you have, for instance, for this is aluminum, and you also have that for, say, diamond. Just for example, that you have different material, and this is maybe for lead. And if you plot this CV as a function of temperature using the regular temperature as your axis, they behave similarly, but they are not on the same line. However, if you plot this as T over T, let's say the Debye temperature, and note that this Debye temperature is related to the material itself. So for each material, it will have its own Debye temperature. So if you plot this against T over Td, then for all these three materials, they will maybe converge onto the same line, right? If you still remember that from chapter 6 or chapter 5. Remember that we discussed this before. So this is a similar universality that if you remove the material-dependent factor, from all these experimental data, they all behave similarly, which means that you can use the same equation of state to describe their behavior. Okay? So the most important thing is to figure out what are the P critical, T critical for all these different gases. So let us propose, Van der Waals, he's a physicist in the past, he proposed this gas model which has been used by many others to describe the behavior of real gas. But recall that for the ideal gas, the internal energy is only a function of temperature, right? Remember that we spent a lot of time discussing internal energy as a function of both temperature and volume. And we say that for gas, especially for ideal gas, the internal energy only depends on temperature. So it's only the function of temperature, right? And the argument for this, the physical picture of that, is because the gas molecules, they are not interacting with each other and they are volumeless. So even when you compress or expand this, this bunch of gas molecules, you are not going to change the internal energy because they don't interact with each other. The internal energy is only related to the kinetic energy of all particles, right? Remember when we talk about the Hamiltonian of the ideal gas, it's only related to kinetic energy. There's no, the potential energy or the interaction terms. Therefore, later we derive that for ideal gas, the internal energy is only related to temperature, which is times n, or depending on how many gas molecules you have. So for ideal gas, it's made of volumeless, non-interacting particles. Therefore, you can say this is like that, because energy is entirely the translational energy of motion, which means that it's the kinetic energy of the particles. Therefore, the modification of the ideal gas equation for real gas needs to include the finite volume of these gas molecules, like what we just mentioned earlier. So the particles for real gas must occupy a finite volume. And the particles of a real gas are surrounded by force fields that are generated by other gas particles. For instance, these gas molecules must be feeling the gas force, the force from other particles. So when those particles are close to each other, you can say that they're experiencing a larger interaction. But if they are far away from each other, of course, the interaction will be decreased. Therefore, there must be a mean field generated by these particles, and that can be filled by each one of the gas molecules in the system. To model that, of course, there are several different ways. And we'll see that the most straightforward way will be adding a correction term in the pressure part. So we've already seen this kind of correction earlier when we talk about the real gas. We have a volume minus some particle volume correction term. But more importantly, we also have this interaction force correction term, which is related to the pressure. So imagine that if there's no interaction among particles, if you still remember how to derive the ideal gas law, the pressure term, the P term, is actually coming from the reflection of gas molecules when it hits the wall of the container, right? But in reality, these particles are not just freely moving around and then impinge onto the wall of the container. There is some interaction with the particles inside the container, which will, for instance, reduce this kind of force hitting onto the wall of your container. So therefore, the real pressure is probably, for instance, actually smaller than the pressure that you think for the ideal gas. And therefore, you have this plus term over here. So A, most of the time, is a positive number. So you have P plus this interaction term to reduce the real pressure value, So to be noted, here the P and V are the measured pressure of the gas and the measured volume of the gas. Since we don't know how large, we cannot really measure the real pressure experienced by these particles. So we're using the pressure measure macroscopically. So the volume and the pressure shown in this equation of state are the numbers or are the values that we're going to measure. So these are the measured quantities. For instance, P, when the problem tells you that the measured pressure of this real gas is, for instance, 1 atm, it means that when you use this equation, you're going to put in 1 over here, instead of assuming that P plus this is 1. Okay? So this is pretty straightforward, that whatever the problem tells you, or whatever P or V they tell you, those are the numbers for the measured pressure or measured volume. And you're going to use that to plug in to the equation of state. Okay? So don't get confused by what the real pressure is or what the real volume is, for instance, for the gas molecules and for the container is experiencing. Those are not really that matters. What really matters is that the numbers that you're going to put in is the measured values. are the measured values. If you're dealing with like more than 1 mole of van der Waals gas, you have to make some corrections because you're having nRT on the right-hand side. So you also have to do some correction on the left-hand side. So I think there are 1 or 2 problems involved, in this chapter that you need to deal with more than 1 mole of van der Waals gas. So please bear in mind that you have to use a different kind of equation to calculate your results. But in most cases, you will be starting from just 1 mole of gas, so you can just free to use this equation. But just sometimes you will be dealing with more than 1 mole. So this is the case. And the determination of these quantities, for instance, B and A, are sort of complicated. But we know that based on the picture that we just mentioned earlier, this exclusion of volume, which is related to B, needs to take the collision into account. So for instance, if you're dealing with this collision of particles, for instance, these 2 particles, let's say when they're in contact with each other, and let's say if each particle it has a radius r, then we know that there's a forbidden zone for the particles to move in, right? This sphere, defined by this orange line, this sphere is the forbidden zone for the particles to move in. So this is the volume that has been excluded by considering a finite volume of the particle. So imagine that if originally these particles are just points, for instance, 1 point over here and 1 point over here, they are actually free to move around, right? This particle can move to just right next to this particle because there's no finite volume. But in this case, this particle, the center of this particle can only stop over here because you cannot move even further. These 2 particles, they are already touching each other. Okay, so the region over here has been excluded. And if you calculate this, the real radius is 2r, so this volume is something like this. So 4 pi over 3, and the radius that you plug in is 2r. Let's say this big r. And but averagely, because this is the case for 2 particles, so in terms of average, for each particle, then you have to divide this by 2. Right? So overall, you'll have something like this. This is it should be something like this, right? This is 8 for, yeah. So eventually, you'll see that on textbook. Also, this is a plot. This is actually from the last version. I think that from this version, they probably take this out. But overall, the volume that has been excluded for each particle is like 16 over 3 pi r cubic. Okay, so this is how they calculate, at least over here, like how it calculates this number. It's by the exclusion of the volume when you consider finite volume of 2 particles. So this is the volume correction part. If we're going to talk about the pressure correction part, remember that originally these particles, they are hitting the container walls, and they will give rise to the pressure. However, right now, we know that there are some particles that are right next to the surface layer. And therefore, there's an interaction between this layer and this layer of particles. And imagine that they're like very densely packed. So they are sort of acting like solids. And therefore, they have attractive force between this first layer and the second layer. And we know that this interaction will be proportional to the density of the particles on each layer. So for each layer, the density is n over v. If I remember this correctly. Yeah, this is the density of each layer is proportional to n over v, depending on how many particles you have and how large the volume you have. So the density of the particles will be n over v. This is the molar density, of course. Therefore, this interaction among these layers will be proportional to the square of this thing. Okay, the square of this thing. So you can imagine that it's proportional to the inverse of v squared, because that interaction is proportional to the density of each layer. Therefore, we can say this is proportional to v squared. So that's the reason why in this term, you typically have a constant over v squared, because it depends on the volume of the system. If the volume is big, then you can imagine that the density of the particles will be small, and therefore the interaction, this correction term should be small. But when the molar volume or the volume is large, this correction term should be significant. Okay, so these are the physical origins of these correction terms. And later we'll just take this for granted and then use this equation to do a lot of different things. Okay, we'll stop over here. Okay. So over here, let us go back to this expression. So van der Waals equation is for real gas is something like this. But this is actually modified from the ideal gas equation. And we know that for ideal gas, it is simply, for 1 mole of ideal gas, it is something like this. And I think the volume correction is much easier for you to understand, right? Because the volume is always the volume that you can measure. And right now, then we modify this into V minus B, which means that we take the exclusion volume into account. Okay, so the right-hand side is still the same as RT, but now the problem is what the pressure should be. And to make sure that the equation is still having an equal sign over here, we need to make sure that the pressure over here is something close to the ideal gas pressure. Okay? But what we measure, which is the pressure on the container wall, is not for the ideal gas. So we have to put in something that will mimic the behavior of ideal gas pressure. So someone approached earlier. So this is my explanation. So the reason why we have a plus A over V squared term here is because we want this term to behave, this pressure term to behave similar to an ideal gas pressure term. So let's say this is ideal, and this is somewhat, can call this also P ideal. But this is the the thing that we measure, right? This P is the pressure that we measure. And we know that this pressure should be less than the ideal gas pressure. Because from what we just argued earlier, so this is a container wall, and these are the particles that we're going to interact with the container wall. And we know that because due to the next layer of particles, there's an attractive force between them. So the real pressure is actually reduced from the ideal gas pressure. So the ideal gas pressure minus this correction term should be the pressure that you measure. Therefore, this P measure should be smaller than the P ideal. And therefore, this will go back to the expression that we put in. Okay, so that's the reason why here you have a positive sign. So every year, when we come back to this sentence here, it seems to be really confusing because for the volume part, V minus B is that available for motion of the particles of the gas, and V is the molar volume which the gas would have were the gas ideal. So if the gas was ideal, V is the volume that you will have. But if you look at the description for P, it seems to be the opposite. So if P is the measured pressure of the gas, then P plus this is the pressure which the gas would exert on the containing wall if the gas were ideal. Okay, so yeah, the logic seems to be quite the opposite. But the reason for that is because we want to start from the ideal gas law, and we already know the volume correction to be something like this, so there's no doubt for that. But we also want this term to mimic the behavior of ideal gas. But what we really measure is the measured pressure. This should be less than the ideal gas pressure due to the interaction between the first layer and the second layer of gas molecules. So this is what this sentence is about. Okay. But the bottom line is that as long as the problem tells you the pressure and the volume, this is the equation that you're going to use because, like I mentioned earlier, these are the measured volume and the measured pressure. Okay. So if you further expand this, this equation will be rewritten into something like this. So in the order of volume, we can rearrange the equation like this. So you have a PV cubic here, and there's a V square term over here, and then 1 time of V, and there's a constant term. So the reason why we write an equation like this is because we want to solve, for instance, volume as a function of pressure and temperature, right? So in this case, typically we don't go through the solving process. Directly, the textbook will tell you what the solution will be. So the solution of equation 8.6, which is the polynomial that we just saw earlier, gives a family of isotherms. So for each solution, for instance, if you fix the temperature, and if you solve for P as a function of V or V as a function of P, remember that if you fix the temperature, which means that this constant is fixed, then you can solve P as a function of V or V as a function of P. In this case, it's probably volume as a function of pressure, right? If you solve that, you typically will get the isotherm, from from this equation. So depending on the temperature, you will get maybe say one solution or two solutions or three solutions, depending on how you solve this equation at the different temperatures. So as T is increased, the minimum and the maximum approach one another until at T critical, they coincide and produce a horizontal deflection corresponding to T equals to T critical, P as P critical, and V as V critical on the PV curve. So what this section is about is, after solving that, if you can, say, plot P as a function of V, again, we'll retrieve that as if T is greater than some critical temperature, the isotherm P as a function of V will behave as just like an ideal gas. And if you reach the critical point, again, you start to see this. However, if the temperature is less than that, you see something like this. So you have a local maximum and a local minimum on this plot. Okay, so it means that you have these 2 points. So this is a local maximum, this is a local minimum. But when the temperature is at T critical, there's only one this inflection point. And again, this corresponds to P critical and T critical. So unlike the previous case, unlike when we talk about these in the previous example, the first example in this chapter, if we're dealing with van der Waals gas, you can actually solve these values explicitly. So in this case, you'll solve that the P critical is related to T critical and V critical like this. So you don't have to know how to solve this, but these are the conditions that you will use for the critical point. So for P critical, we can solve that value. And we further know that partial P, partial V, and the second derivative of that point is also 0. So basically, we use the conditions that we learned earlier, that the slope of this point is 0, and also the curvature is 0. Therefore, based on these three expressions, we can solve the numbers for these three quantities. So this is the case when you're dealing with van der Waals gas. The good thing is that you can solve these three quantities explicitly. So as long as you know, like the experimental values for T critical, V critical, and P critical, you should be able to express A and B explicitly. Therefore, you can write the equation of state with all the numbers known. So the idea is that when you're dealing with a new real gas, you typically will just change the temperature and then measure P and V. And until you reach this point, T critical, so basically you know what the T critical is, and then you measure your P critical and V critical. So once you know these three quantities experimentally, then you will be able to get A and B by using the relations that we derived. And once you know A and B, you should be able to write the equation of state for this real gas. Okay? So the the process is from experiment, you determine T critical, and V critical experimentally. And then you can determine A and B by using the relations, or you can say equation 8.7. And then you can write down the equation of state. Therefore, we can start doing some other calculations based on the equation of state. For instance, you want to calculate Gibbs free energy, so the change of the entropy. Later we'll see that. As long as you have the expression for equation of state for this real gas, you should be able to do that. Okay, so the process is important. Determine this experimentally, and then determine A and B based on these three relations, and then later write down your equation of state. But typically, for the questions that you will see later in this chapter, they will just give you the numbers for A and B, and you can directly start from here. So you don't have to worry about calculating A, B, or these constants from the experimental data. Typically, the problem will already tell you these information, so you don't have to do that. So the values of A and B can be obtained by fitting the van der Waals equation to experimentally measure variation of V and P, which is this for real gas. Okay, for real gas. So let us go back to this plot over here. This is similar to what I plot on the blackboard. That when you increase the temperature, again, if the temperature is higher than this critical temperature, then the behavior will just be similar to, for instance, ideal gas. You'll just have this isotherm as a very monotonic increase when you decrease the volume or increase the pressure. However, if the temperature, for instance, the critical temperature here is T3, then you start to see this inflection point. And below that temperature, you'll see a local maximum and a local minimum. Okay? And you'll see this kind of behavior as you further go down to lower temperature. But this is an interesting scenario, because if you take this section, for instance, on this plot, it will be this section, from the local minimum to a local maximum. If you take this section into account and you look into that more carefully, you'll see that the behavior of gas along this section is actually unphysical. And the reason why I say this is unphysical is because if you know the compressibility, remember that this is an isotherm, which means that the temperature is fixed. And for this one, the slope of this one is partial P partial V. Right? And partial P partial V should always be less than 0. It should be a negative quantity. So for all matters, for all kinds of materials, partial P partial V should be less than 0, right? But over here, you have a positive slope. Over here, for this section, this is positive, which means that this part is unphysical. So for real matter, this cannot happen. This cannot happen. So this model seems to be okay, but at least in some region, for instance, starting from F, G, H, I, J, if you go back, if you just remember the case that we mentioned earlier, we start from a larger volume and then we compress the gas. And if you go from F point to J point, this evolution is unphysical. Right? If you still remember compressibility, we know that when you increase the pressure, the volume is always decreasing. right? So that's the reason why I said this compressibility is always negative. I mean, through the definition, we put a minus sign here, so this term should always be positive, but partial P partial V, or you can say partial V partial P, should always be a negative value. Because when you increase the pressure, the volume can only become smaller. Okay, so which means that this part is unphysical. And we need some other method to resolve this issue. So let us go back to the, let us look at this evolution from the point of view of Gibbs free energy. So first of all, the reason why we need to look at Gibbs free energy is because the curve that we just mentioned, this part, has no physical significance. So we need to find something to replace this part. So let us consider the Gibbs free energy. And we know that the Gibbs free energy at a constant temperature is written as G as a function of pressure, because now we're only changing, for instance, the pressure and also the volume. And the temperature is fixed. And dG is VdP, right? So recall that. So always remember this. And in the case of constant temperature, this is 0. So you are left with dG as VdP. This is a very important expression in this chapter because, as you can see, we're dealing with isotherms a lot. So if you're dealing with isotherm, dT is 0. So the change of Gibbs free energy is V times the change of pressure. Okay, so right now, what we want to do is, for instance, start from this point, and then we start to see the evolution of Gibbs free energy. For instance, starting from here. Let's say this is point A, and then we start increasing the pressure and then decreasing the volume. Let's see what will be happening to the Gibbs free energy. So we know that starting from this point, the Gibbs free energy is the Gibbs free energy at point A over here, state A over here, plus from PA to some certain pressure. So this is the expression of this equation 8.8. Basically, we start from this point. Let us assume that there's a Gibbs free energy called GA. And then when we change the volume and also change the pressure, we start to see this evolution. So a better way to plot this is actually rotate this by 90 degrees. Because right now we're dealing with volume as a function of pressure. So if we rotate this by 90 degrees using volume as a function of pressure, this will be something like, well, maybe like this. Right? If you rotate this by 90 degrees. And let's say this is the point A that we're dealing with. And say B is here. What else? C. And there are the too many points. E, G. Anyway, something like this. And actually, the most important points are D, H, and L. So let me mark those 3. So D is here, H is here, and L is here. And note that these 3 points, they're aligned with each other. So you have this point D over here, H, and this is L. So if you rotate the plot by 90 degrees, then you can know how to calculate this. So this is just a number that we're going to assume there's a certain number, and then we'll start from this point. This is pressure A, right? If you go down, this is pressure A. So depending on the pressure, you can do this integration. And this integration is actually just by counting the, measuring the volume, below this line. So for instance, if I start from point A to B, then I'm just measuring the volume underneath this. So for instance, the Gibbs free energy at point B is GA plus this number, and this number corresponds to this volume over here. Right? Should be straightforward. And more importantly, if you keep going, you'll see that this volume will be increasing up to this point F. And then we'll go back to this point. What is this? This is J. So the area is actually originally increasing, and then it will go backwards, decrease by a little bit, and then increase again. Right? So imagine that the line, the line that we're going to do the integration, for the area, will expand from A and then to B, C, D, E, F, and then that is the point when this area is reaching its maximum, and then it will decrease by a little bit when it is retreated back to point J, and then it will increase again when we keep increasing the pressure. Okay, so shouldn't be hard to understand. So therefore, this long list of areas, like if you want to take the different section into account, like I just mentioned earlier. Therefore, if you plot the Gibbs free energy as a function of these points, like depending on which point you're stopping at, you'll see this kind of increase and decrease. We start from this point, which is GA, this number. Okay, and when we go to point B, it's increasing, right? The area is still increasing. And it will keep increasing when you reach point C, D, E until point F, like I just mentioned. When the line is over here, when your line is over here, your area is maximum, because the area that you have is this whole thing. So your Gibbs free energy is GA plus this area underneath, right? GA plus this area underneath, if this is PF. And therefore, you're reaching a maximum point here. When you go further through this isotherm, this line will go back to point J. So you're actually back to this point. So the area you have is actually this whole thing. Is something like this. When you stop at point J, which is this point over here. So during that process, your Gibbs free energy is decreasing because you are subtracting this area that you already have. So your Gibbs free energy is decreasing, and the value will be decreased from F to this point J over here. So the Gibbs free energy for point J is less than that when you're at point F, because the area is smaller. But once you reach this point, and if you go further, you know that you're increasing the area a bit by bit, right? If you go a little bit further, and then even more, then you keep increasing your Gibbs free energy. Therefore, you start to see a return, of Gibbs free energy by moving up. And previously, I said there are 3 points that are important, like D, and this point H, and this point L. And they are on the same line. And the reason why I said they are important is because the area here and here are the same. So when you increase and decrease and you return to this point, your Gibbs free energy coincide with each other. So there must be a point that, for these 3 points, the Gibbs free energy are the same. So this is what we call the Maxwell construction. That we figure out what will be the area, or what will be the line, such that the area here is the same as the area here. Okay. So if I plot this on another plot, which is obvious. We want to figure out if there's a line to make sure that the increase of Gibbs free energy is the same as the decrease of Gibbs free energy during this calculation. So if we can do that, it means that if we start from here and we stop at this point, say point D, and if we just go down through this point H and to this point L, then on this line, we know that the Gibbs free energy will be the same, right? So the process that I just mentioned, like starting from here, say A to D to H to L to, let's say, O over here. Which means that you start from this vapor phase over here, and you stop at this point D, and then the condensation will start. The condensation will start. And then you don't go through the lines here, here, and here. You just go straight to the liquid line. So for DHL, it will spend some time to evolve from here to here, but we know that over here the L point corresponds to the liquid phase over here. Okay, so for this line, it is the liquid phase. And if you remember, when we talk about phase transition, so this is Gibbs free energy, and we know that this value over here is, for instance, pressure. We have a plot like this before, right? And we say this is, let's say this is vapor, and this is liquid. So the evolution is from vapor to liquid. Right? Only in this case, you have, if you really go through the calculation based on, this isotherm, from the van der Waals gas, the evolution is from here back to here, and then to this line. But we know that based on the assumption that this is real material, or real gas. Therefore, you have to rule out the unphysical part, which is this line over here. And we know that the Gibbs free energy, when you move from one state to the other, it will just go through this lowest Gibbs free energy part. So basically, this won't go up. And therefore, it will start from A to D, and it will directly evolve from D to H to L, and then go through the point O. Okay, so this is an important construction. So this is artificially constructed to make sure that the area here is the same as the area here. So you can imagine there are several different lines, right? You can pick this line over here. But the increase of the Gibbs free energy won't be the same as the decrease of the Gibbs free energy if the line is constructed this way. So there's only one solution for this kind of construction to make sure these two areas are the same. And therefore, the Gibbs free energy here will be the same as the Gibbs free energy here, because you increase that by this amount, and then you decrease that by that amount. So this construction make sure that this is the same as this one. This is called the Maxwell construction. So this is artificially made because we know that if you just solve the equation of state, this is the line that you will have. But we know that this part is unphysical. Therefore, we need to make a cut line to make sure that the Gibbs free energy is the same, and then the evolution will be from point D to point L, and then it will just go through this line with the same Gibbs free energy. Okay, so this is what the Gibbs free energy will look like if you just use that equation of state. Okay. So this is the Maxwell construction that I mentioned. And more importantly, this Gibbs free energy at the point D over here will be the same as the Gibbs free energy at point L. And this corresponds to the Gibbs free energy of vapor. And this corresponds to the Gibbs free energy of liquid. Because we know that here it is the vapor phase, and here it is the liquid phase. And the process here, from here to here, is the condensation. And therefore, for a condensation process to take place, the Gibbs free energy will be the same, on the two ends of, or along this line of isotherm. So this section is about. Seems to be complicated, but once you know what Maxwell construction is, this should be pretty straightforward. So for different isotherms, now you can rotate this back to its original configuration, which is pressure as a function of volume. Then you'll see this kind of different kind of isotherms for different temperatures. And for each temperature, you can define this kind of line to make sure that this area is the same as this area. So when you move from this point to this point, there's no change or increase or decrease in terms of Gibbs free energy. Okay? And of course, when the temperature is beyond some critical temperature, there's no need for Maxwell construction because there's only one phase and there's no phase separation. So you don't have to worry about that. So please go through this more carefully. This is a very important construction. I probably, like if you took thermodynamics before, general chemistry, some professors, they will mention this. And I think this is a very common practice, for discussing real gas. And in fact, if you look at the evolution of Gibbs free energy as a function of pressure, but for different temperatures, you'll see that above this critical temperature, then there's no separation of Gibbs free energy lines. There's just one Gibbs free energy line because there's just one phase. which is the supercritical fluid, or you can say it's vapor, or you can say it's a liquid, which means that there's just one phase. But below the critical temperature, which is in the regular condition, you'll always see this kind of two lines. You have the line for vapor phase, and you have the line for liquid phase. Okay. So these are just the expressions for, the descriptions for the figures that we saw earlier. So the variation of P saturated with temperature, as you can see from the previous plot, when you increase the temperature, the saturated vapor pressure, which is the point over here, is increasing. Recall that, from this plot, we know that this pressure here, this point, corresponds to the saturated vapor pressure of that gas or of that liquid. But when you increase the temperature, this saturated pressure will also increase. But we derived this actually in chapter 7. Like there's this increase of, when there's an increase of temperature, there's an increase of saturated vapor pressure. We use, I think in the last chapter, we used Clausius-Clapeyron equation to derive that. In this case, it's the same. When you increase the temperature, you will see that from the Gibbs energy plot that the saturated vapor pressure will also be increasing. And if you use van der Waals gas equation of state to estimate log P as a function of 1/T, you'll see that there's a linear trend. And recall that from previous chapter, we use Clausius-Clapeyron equation. We derive this as the nature log of P is a function of A/T, and then there's a B times log T plus some constant. And typically, you can also say that because we derive this by using the enthalpy, the enthalpy for this phase transition is typically some constant plus some term that is linearly related to temperature. If you still remember the example from last chapter, there's this delta H is a constant plus something that is related, linearly related to temperature. But the bottom line is that this saturated vapor pressure is related to A/T and then some log T term. If you assume that this log T term is small, then you can say nature log of the saturated vapor pressure should be proportional to the inverse of temperature. And as you plot it out, you'll see that if you use van der Waals gas to estimate, it will be a linear trend. But for the real gas, when you measure that, there's this slope as well. It's linear, but there's a deviation from the van der Waals prediction. And the deviation will become bigger and bigger when you decrease the temperature. So this is 1/T. So over there on the right-hand side means that you have a lower temperature. So when the temperature is becoming lower and lower, the deviation from van der Waals gas is becoming larger and larger from the real gas. Which means that the van der Waals gas is better for, say, high temperature approximation. So this plot actually essentially tells you that the van der Waals equation is better used at higher temperatures. Because when the temperature is high, as you can see that these two lines will start to converge to each other. Okay, and also note that the slope for either the measured gas or the van der Waals gas corresponds to a constant here. Corresponds to the constant here, the constant A. So the van der Waals equation actually predicts the values of vapor pressure which are higher than the measured values, although the difference between the two values decrease with increasing temperature. So when the temperature is increasing, when you go up to higher temperatures, the prediction will be better. However, if you go down, the van der Waals equation will have this overestimation. And also from the slope, you can actually extract the evaporation enthalpy, or the latent heat for evaporation, which is this value. And the reason why you have m and r over here, the m is from the slope that we define over here. So if you have a slope which is this, we know that the slope is if you define it as m here, then it's m over t. So here, delta ht is minus mr, right? So that's the reason why you have minus mr here. And the reason why you have 2.303 is because there's a conversion between nature log and the logist using 10 as your base. Okay, so if you're using log, the regular log, while comparing to the nature log, there's a conversion ratio. Okay, so it's not just directly using m over here. Okay, so you're not just replacing a with m, but you also have this conversion between nature log using like e as your base, and also the regular log using 10 as your base. So there's this 2.303 conversion ratio. This is not very important, actually. I think that this part is just trying to show you that the one van der Waals gas can sort of retrieve the behavior of the real gas, at least in this fashion. What is more important is that if you look at the liquid to vapor phase transformation, if you write down the enthalpy for this evaporation process, it's actually the enthalpy for a vapor minus that for a liquid. And therefore, you know that there's contribution from internal energy change and also the change for the PV term, right? And in this case, for instance, if you're dealing with constant pressure process, then the P is a constant. And right now, we're going to include the discussion that we had for several times. In chapter 2, actually, we already discussed this partial U, partial V at the constant temperature. We know that for ideal gas, this term is 0, right? For ideal gas, since the internal energy is independent of the volume, therefore, for ideal gas, this partial U, partial V, we tried several times, several different methods to prove that is 0. Right? This can be easily proved because we already know that this is, so this is a T times partial P partial T. And if you use this is ideal gas, right? If you use this, if you plug in, this will just be 0, right? This will just go back to 0. So for ideal gas, this is the case. But for real gas, this term is not 0. So if you use van der Waals equation, and if you use this partial U, partial V as at fixed temperature, it turns out to be A over V squared. So this corresponds to that correction term we have for the pressure. So for, let's say for van der Waals gas, also know that this is sort of very common abbreviation for writing down like van der Waals, because van der Waals materials are very popular these days. So people typically come up with different kinds of abbreviations. So this is one of them. For van der Waals gas, this is not 0. And we know that you can start from the same thing. And this turns out to be A over V squared. Which means that the correction term that we introduced, for the pressure part is actually related to the internal energy change when you change the volume. Right? And originally when we discuss the ideal gas, we know that there's no interaction among particles. So partial U, partial V will be 0 because there's no interaction. Okay? But for van der Waals gas, because we intentionally put in this term, so that's the term that we will retrieve over here. And therefore, if you do the calculation, if you integrate this, we know that the internal energy is a function of A over V, because if you integrate this over V, you will have A over V as a minus sign over here. And there's a constant that is related to temperature that, we don't worry about that at this point. So if you, again, calculate this latent heat for evaporation, then you have the P times delta V term. But at the same time, you also have this A over V between before and after the phase transition. So eventually, the form will contain two terms. The first term is related to this interaction, which is A over V vapor and A over V liquid. And the second term is the original enthalpy change, which is P times delta V. And more importantly, we know that when the temperature is close to T critical, the molar volume of liquid should be the same as the molar volume of vapor because there's no distinguishment between these two, right? The vapor and liquid, they look the same. If we're using the van der Waals gas, and we know that beyond the critical point, those two phases are acting like they're just one phase. So those two things are the same. So if these two values are the same, it means that if you plug in the same numbers, this term will be 0. Okay, so which means that there's no latent heat for this transformation. So this is consistent with what we expect because there's just only one phase. So there's no phase transition, therefore there's no latent heat being involved in this process. And therefore there's only this continuous change in terms of density when your fluid or when your vapor or liquid is higher or is close to the critical temperature. Okay, so this part is about this. But of course, although van der Waals gas, this equation is established by considering different factors, for instance, volume exclusion and also the interaction among gas molecules. But typically, we still determine A and B by using empirical method, which means that if you still remember, like I mentioned earlier, we start from experiments, and then we determine P critical, T critical, and V critical. And using those numbers, we determine A and B. And then we use those two numbers to write down the equation of state. So typically, the problems that you will see in this textbook is working this in a reverse way. It just gives you the numbers of A and B, and then asks you to calculate different things. For instance, P critical and V critical. But in reality, typically, it's the opposite way. You start from experiments, and then eventually you determine A and B using this empirical fitting. Okay, so that's the difference between reality and what we learn in textbook. Okay, so I'll stop over here, and then we'll continue to look at different kinds of real gas equations. So actually, we already see that the van der Waals gas has its limitation, right? If you look at the comparison between the real data and the van der Waals gas results, you'll see that there's a huge deviation. So the people came up with different kinds of models. For instance, There's one like which involve an exponential term, and there's also this one with a slightly different expression while compared to the van der Waals gas equation, because here you have a temperature term over here. But the most common one, actually this is a very classical one, is proposed by Cameron and Onnes. This is called the virial equation, or you can say the Onnes equation. And Onnes is a Dutch physicist who discovered superconductivity in the early 20th century. So his most famous quote is that from measurement to knowledge. So he believes that all the knowledge should be obtained through measurements because he's an experimentalist. So basically, I agree with him. So I typically don't believe theorists, and I believe that most of the things, the facts, should be generated by experiments. So Honest, in the earlier 20th century, he proposed that for all kinds of gas molecules, you can just use one equation to describe their behavior, which is called this virial equation. But you will see that this is too general, because basically it's just a polynomial expansion for all kinds of terms. So basically, if you still remember that we discussed this factor z called the PV over RT, and we know that for ideal gas it will be close to 1, right? And previously we know that if you can use a linear approximation, then you probably can describe some behavior of gas in the low pressure regime. But what if you go up to higher pressures? So Onnes proposed that why don't we just include more terms? So this is what typically physicists will do. Like if 2 terms or 1 term cannot explain your data, you just include more terms until you can fit all your data that you have. So this is a very experimentalist approach. You just introduce more terms. While for theorists, typically they want to reduce the terms. Okay, for instance, like van der Waals equation is very elegant. It's very, there's no a lot of terms that has to be involved. But in this case, for Onnes, Cameron Onnes, for his expression, you actually, if you want to include all of them, you have infinite terms. So typically, we will write down maybe the first 2 or 3 terms, and it will say maybe we'll just stop over here, stop at the p squared term. And typically, if the pressure is low, then we know that if p is small, this is a small number while comparing to the second term. So you can ignore that. So we'll go back to this original 1 plus some prefactor times p, this linear behavior. So the idea of Onnes' virial equation is that we know this for real gas is something like this, right? And in order to describe all these kind of different behavior, Onnes suggests that this should include all different kinds of dependence, such that you have the linear term, you also have the nonlinear term, you also have p to the 3 terms, and et cetera, et cetera. But of course, we know that when p is close to 0, this z will be close to, say, 1 plus bp, or you can say it's close to 1, depending on how small this is. Okay, so this is by writing this function z as a function of, this factor z as a function of pressure. But you can also expand this polynomial by using a volume. So if that's the case, you have the expression like this. So this is not that common while comparing to this one. So let us just focus on this one first. Okay. So there are some definitions. I mean, the term PV is covarial. It's not that important. It's just the name of that. And these B or B prime, depending on which form you're using, these factors are called the first virial coefficient, and using the same approach, like we can say C and C prime are the second virial coefficient. So this is the first one. This B is the first virial coefficient. And this is the second. This is the third. And these virial coefficients are functions of temperature. So although we write these down as like a letter B, C, or D, but in fact these are functions of temperature, which means that when you change the temperature, these factors will change as well. So of course, a better expression will be something like this. These are a function of temperature. As you know that typically we just plot this curve for a fixed temperature. When you change the temperature, this line will be different, right? So for changing to different temperatures, this line will change, which means that the coefficient will change with respect to temperature. And more importantly, of course, when the pressure is close to zero, and when the volume is close to infinity, which means that the density of the particles are very, very small. If that's the case, then PV over RT, or Z, will be close to 1. So the behavior will be close to ideal gas if you are in this extreme case. So when we talk about this virial equation, or this expression proposed by Honest, actually we're going to use this to calculate, for instance, the Gibbs free energy when you change the pressure for the real gas. So therefore, the next section, we're going to talk about some thermodynamic treatment for non-ideal gases. But let us look at the thermodynamic treatment for the ideal gas again. So if you're dealing with ideal gas, we know that if we want to know the change of Gibbs free energy, for instance, let us consider this at a fixed temperature. This is 0. So dG is VdP. And we know that for ideal gas, the volume will be RT over P, right? So if you plug in, eventually you'll have this expression. dG is RT log P. If you want to memorize this, be my guest, but this is very frequently used. So for ideal gas, this is a very frequently used equation for some calculations. So please remember this. But for non-ideal gas, of course, we know that we cannot just directly convert this into RT over P. We know that this is always true, but this part depends on the type of the gas. So only when you're dealing with ideal gas, you can make this jump. But this is always true. As long as you are dealing with a constant temperature process, you always start from this equation. Okay. So in this chapter, you'll see a lot of calculations based on gas, and it asks you to calculate the change of Gibbs free energy. This is where you start. So no matter if you're dealing with a real gas or an ideal gas, you always start from here. But for ideal gas, you'll end up with d log P. But for non-ideal gas, you can derive some other types of forms using this equation. So of course, for non-ideal gas, we also want to, if we still want to use this equation to calculate, we typically introduce a function called fugacity. And this fugacity is defined by this equation. So you'll see that for ideal gas, it is RT d log P. And we do that for non-ideal gas. And this is the definition of fugacity. We know that for non-ideal gas or for real gas, this is not the case. But if we want to use the same equation, we will use a function called fugacity, and then such that we can write down the same, or you can say a similar equation like this. So please remember, this will definitely go into exam, so please remember that the definition of fugacity is expressed as this. Okay? So it is by treating the gas like an ideal gas, only that the pressure is replaced by this function called fugacity. And we know that if the gas is, for instance, in the low pressure condition, when the pressure is close to zero, we know that this fugacity should be close to pressure. So when pressure is approaching zero, then F should be close to pressure. So this fugacity, which is a function that we use to calculate Gibbs free energy, should be similar to pressure when the pressure is close to zero, because now the behavior will be approaching an ideal gas behavior. So this is what this is about. The fugacity will be close to pressure when the pressure is close to zero. And in that case, the Gibbs free energy, delta G, is calculated by this G0 plus RT log F. And the reason why the G0 represents the Gibbs free energy for F equals to 1. So G0 is the molar Gibbs free energy of the gas, and it's standard state. So it is defined, in this content, it's defined as the state in which F is 1 at some certain temperature, at a temperature T. So all these are from this equation. So that's the reason why I think in chapter 7, I stated that this is important. So depending on you're dealing with constant pressure or constant temperature processes, if you want to know what DG is, you always start from here. In this case, you're dealing with a fixed temperature, so this term is 0, so you have DG as VDP, and then you can calculate these. Okay. So starting from here, the textbook I think is kind of hard to understand, but I'll go through the textbook, the materials in the textbook, and then I'll summarize that using my own way. So the textbook actually asks you to consider a gas which obeys the equation of state like this. So V is RT over P minus alpha, and alpha is a function of temperature. So if you look at this more carefully,
you'll see that this is actually very similar to what we just learned for other type of gas models, right? Because here it asks you to consider the volume is, so this is the ideal gas, right? But it asks you to consider an extra term. And this extra term is a function of temperature. So this is actually the same as if you move this to here, and if you further move this to here, it is something like this, right? So if you still remember from the very beginning of today that we've already seen this kind of expression before, right? We saw P times V minus B, so RT earlier, right? We've already seen this before. So it is by using this and then just rearrange that into this kind of different form. I'm not sure why the textbook still using like alpha here, but it's essentially the same as what we used earlier as minus b, right? So this is essentially the same. But just in this case, at least in this part, it's using this weird expression. But we know that this is a temperature-dependent factor. So this alpha in this content, it is defined as a measure of the deviation of the gas from the ideal gas. So recall that, again, using this Gibbs free energy as VdP at a constant temperature, and we can start to rearrange these things. Okay? First of all, dg is VdP, and we know that dg is also, or you can say VdP is RTD log F. So, as I mentioned earlier, this is always true, right? And also, by definition, we know that dg is RTD log F, and F is fugacity. Because we're dealing with non-ideal gas, so that's the reason why we cannot write it as d log P. So we use d log F. So this is by definition. This is always true. And so we can link these two together, and that's the reason why you have the equation here. And therefore, if you put this back in, so if you use this volume, and if you write it down over here, you will get this. So let me do that here. So if we use this, you'll see something like this. Okay, and moving terms around, of course, you have minus alpha t dp over here. And for instance, if I move this to the other side, this term to the other side, we have RT d log F minus P dP, right? And this is just d log P. Therefore, minus alpha is F over P. So this is what this equation comes from. right? Because you have alpha over here, you have RT over here. If you move this to here, you'll see the same thing. Okay, so it should be pretty straightforward. And if you integrate, this equation between states from P equals to 0 to P to some certain pressure at a constant temperature, again, all these discussions are based on fixed temperature. If you do that, then we know that when the pressure is 0, close to 0, F and P are essentially the same, right? So this term is natural log 1. So this term should be 0, okay? So eventually you're left with a natural log F over P equals to minus alpha P over RT. So eventually you'll have this expression, and now you can express the ratio between fugacity and pressure as this exponential term, okay, as this exponential term. So you can see that, when the temperature is high, the fugacity is also the same as pressure. So there are some extreme cases. Right now we have the final expression of this ratio, and it's related to exponential is minus alpha over t. First of all, you'll see that when the pressure is 0, when the pressure is close to 0, exponential 0 is 1, right? So based on this expression, we know that this is consistent with what we expected. When pressure is 0, F over P should be close to 1. And also, when the temperature is high, say this term is big, so this is also 0, and this is also close to 1. So again, this is consistent with what we learned earlier, that when the temperature is high, much higher than the critical temperature, or when the pressure is much lower than, say, 10 atm, then we know that the behavior of the gas is close to ideal gas, right? So the fugacity will be close to, or you can say fugacity will be close to the pressure. However, if the temperature is low, it is it's at the regular temperature, and if the pressure has some normal pressure, then we know that F and P will be different. And the ratio between them should be expressed by this exponential term. So we can further simplify that. So in order that alpha can be taken as being independent of P, the deviation of gas from ideality must be small. So let us assume that this deviation is small, then this exponential term can be further simplified to 1 minus alpha P over RT. This is just Taylor expansion, right? And we take just first two terms. So if we do that, you'll see that F over P is approximately this term, right? Originally it is this exponential term. If the deviation is small, let's say just small, then this is close to 1 minus alpha P over RT. So if we do that, you'll see that this ratio eventually will be simplified to just PV over RT. So this is the same as Z, right? Our original definition of the factor Z is PV over RT. So it will be the same as F over P. So in this case, if we use that, and if we plug in the original expression So alpha can be replaced by RT over P minus V. This will be the same as PV over RT. And this is the factor Z that we mentioned earlier. Right. So you'll see that these different definitions, they all have the same expected result. Right? When P is close to 0, T is infinity, F over P is close to 1. Therefore, this factor Z is also close to 1. When we first see this definition of Z, we already discussed about that. And more importantly, you'll see that later, that if you still remember from the V-real equation, this is 1 plus BP plus some CP squared, something like that, right? And again, if similarly, you only consider the first two terms, so you ignore the square terms and the third order terms, you'll see that this is the same as this expression, right? We mentioned that this B is a function of temperature. It is because alpha is a function of temperature, and you also have a T over here. So for V-real, if you want to compare this with the V-real equation, you'll see that this is the B from the V-real, should be the same as minus alpha over RT, just to compare. So you'll see that all different kinds of expressions, they are all consistent with each other. And these are just some description to talk about the result that we just derived. If the gas behaved ideally, then the ideal pressure will be RT over V, right? This is if the gas is ideal. But we already know that F over P is something like this. So we can replace this by P over P ideal. Therefore, P squared will be the product of fugacity times the ideal gas pressure. So this is not very useful at this point. Well, probably not very useful for the rest of this semester and also the rest of your next semester. But the reason why it wants to show you this is because it wants to tell you that the actual pressure P of the gas is a geometric mean of its fugacity and the ideal pressure. So fugacity is something that is defined as pressure, but it's not really pressure, right? And right now we have F over P close to P over P ideal. So if you just look at this equation, you'll realize that so the ratio between fugacity and the pressure that I measure is actually the pressure that I measure to the pressure that is in the ideal case. So what's this? So this is actually, fugacity is actually a measure of how much your gas has been deviated from the ideal gas. Because the percentage change of fugacity to the pressure that you measure is the same as the ratio of change of P measured to the P ideal. And therefore, you'll say that this F times P ideal is P measured squared, or we can say the measure is F plus P ideal. So this expression is not that useful, like I mentioned, but I believe in this textbook, maybe there's 1 or 2 questions related to this. They ask you to calculate the relations between fugacity and the measured pressure. But this, I believe, at least it's my personal view, that it's not very useful. So the percentage error involved in assuming that the fugacity is the same as the pressure, is the same as the percentage departure from the ideal gas law. So this is what I just mentioned earlier. If you assume fugacity is the same as the pressure you measure, then the error that you made will be the same as by assuming your measured gas is ideal gas. Okay? So if you measure something and then you assume that it is ideal gas, then when you calculate the fugacity, the error that you made will be the same as by assuming that if you use So if you're dealing with a real gas, theoretically, in reality, you should use this one. But if you use this one, then the error that you cause will be the same as by assuming your gas is ideal. Okay? So all the errors that can be generated during your calculation is due to the assumption that you assume your gas being ideal. But in reality, you should use fugacity to calculate delta G, and you should use P measure to calculate, for instance, the gas equation. Okay, so please bear in mind that whenever you want to calculate Gibbs free energy for real gas, you use either this or this. Use these two. So if we express F, this fugacity, in terms of compressibility factor, this factor Z that we just mentioned, which is PV over RT, we'll see that this is not a very good starting point, but let's use D log F over P. And we know that it is minus alpha over RT times dP. I've already erased that, but if you still remember that. So eventually you arrive at this D log F over P being Z minus 1 over P times dP. So this expression can be used to calculate this fugacity. So as long as you know the expression of Z for your function, then you can calculate this. Okay, you can calculate this D log F over P. So like I mentioned, earlier, that this textbook used a lot of different kinds of expressions to talk about the same thing. And this is an example. Because if we start from a very simple expression, for instance, the Virio equation, we'll suddenly see this in a much more simpler way. But if you're dealing with log F over P, if you do the integration from pressure 0 to pressure to, some certain pressure, you'll see that the integration can be done by this. And the textbook tells you that it can be evaluated by a graphical integration of a plot of Z minus 1 over P versus P, which is not that useful at all, because most of the time you will know the expression for Z explicitly. So basically you will plug in the expression of Z into this equation and then to calculate log F over P. And so more important is the second approach is Z. If you already know what the expression of Z is as a function of P, then you can plug in that back to the equation. For instance, Z being for the Virio equation. So if you know this, then you can calculate Z minus 1. Right? So Z minus 1 is simply, we know that for Virio equation, it is 1 plus Vp plus Cp squared. So you know how to calculate Z minus 1. This is just Vp plus Cp3, Cp2, blah, blah, blah. And divide this by P. will be something like this. And therefore, if you want to calculate this, it's simply integrating this over dp. So depending on like where you want to start, if you start from here, then eventually the delta G that you have will be, can be expressed as something like this, if you want to calculate delta G. So let me skip something first. If you want to calculate this, we already know the expression of Z. If you plug in, then you can calculate this based on what I just wrote down. So eventually this will be back to the original expression, right? Sorry, this is having a 2 over here. So if we want to calculate dg, it is RT d log f here. And if you can decompose that into 2 terms, so this is the term for the ideal gas part, and the part with fugacity is this d log f over p, and we already know that d log f over p is this term. So if you plug in that and add these 2 up, this will be the expression. So it's like they're changing all those terms together and doing this in several different ways. So I'll do this. If you don't want to read textbook, just read my note. It's much simpler. I don't know like who, I mean, the guys who wrote these textbooks must be having a very weird way of thinking. So let me start from a very simple assumption. So overall, like what we want to calculate is delta G, okay? So we want to calculate delta G. And we know that dG is V dP. Like I mentioned several times, this is always true. And this is also always true because this is the definition of fugacity. So for constant temperature process, whenever you want to calculate calculate the change of peak free energy, this is your starting point. Okay, this is your starting point. Okay, and we know that for the real equation, this compressibility factor is PV over RT is something like this. So if we want to calculate this, there are several different ways. For instance, if we want to calculate this, we can express volume as a function of pressure, right? We can write volume as a function of pressure and then do the integration. That's one way. Okay, that's one way. So if we do that, this volume is RT over P 1 plus something like this, right? So you have the first term being inverse of P, and the second term is a constant because the P and the P over here, they cancel out with each other. And this term is proportional to P because you have 1 P left. So if you do this, And we know that V dP will be this is volume, and dP over here should be the same as RT d log F. Right? And it is pretty straightforward that the first term is something related to log P, right? Because you have this dP over here and this 1 over P. Therefore, d log P, sorry, let's remove RT from both sides. So you have P integrate over dP, so this is just d log P for the first term. And then you have B d log F. Okay. So we already have right now we already have an expression for d log P and d log F. So the connection between these two, or the connection between these two. So now we can write log P over F. So this is the thing that we want to retrieve, right? This log F over P or log P over F, whatever. Let me close this one. This one. So d log F over P. So if we move this term to this side, you'll end up with and this is integrating, let's say, over dP. So if you do the integration, of course, then you will get the expression that we just saw earlier. Right? This will be BP plus P squared. Okay, so this is what you will see if you're using, if you just directly start from the definition. And it should be it should be more straightforward. It should be more straightforward. But of course, eventually, if you're trying to calculate dg or delta g, the result will be slightly different because actually this is already a good expression for that. So in the textbook, it uses a very strange way. So the way that we are using right now is using VDP, right? But the textbook uses a very different way. Originally, we should use RTD log F. but the textbook use it is actually something like this. So that's the reason why it's being very confusing, because it's trying to calculate this first, and then add this original log p term back to this. But in fact, you can actually just use this to calculate, right? So as long as you know what VDP is, you don't need to go through this process. So later you'll see that in this textbook, at least for the quantitative problems, we typically the problem will typically give you this, or some other types of equation of state, and then you just go from this path. You just use VDP and then you calculate the change of Gibbs free energy. You don't have to use this weird expression, or dividing, or decomposing one term into two. But of course, if you want to do that, this is the way. If you want to calculate log, f over p or d log f over p, then it is here. It is this term. Okay. So let me write over here. So if you want to calculate dg just directly from here, we already know that V is something like this. So you can just use this. And then do the integration. So you'll see that this is V. So if you want to, again, separate the terms, of course, you again have this RTD log P term, but you also have the rest, right? Like B times R times T, and this is CRT P, because it is divided by 1P over here. So eventually you'll use this to calculate the change of Gibbs free energy, or delta G over here. And of course, if you're smart enough, you'll readily see that, like I mentioned before, this, let's say, this part is minus alpha t, right? So in the textbook, like I mentioned earlier, this part can be considered, if you're using V-real expression, the rest of this part can be considered as the minus alpha or the alpha t that the textbook mentioned earlier. So if you do that, and if you go through a calculation, you'll see that all the things are actually the same. So the bottom line is that whenever you're dealing with a problem in this chapter, you start from here. You start from here. So if you go through all those information in a textbook, it's actually kind of complicated. But the bottom line is that whenever you want to calculate dg, you start from here. Typically, the textbook won't tell you what the fugacity is. There are some rare cases. There are some, I think, one or two problems that is related to fugacity, but they are not that common. So typically, if the problem asks you to calculate the change of Gibbs free energy, it will give you the expression of gas as a function of either pressure or the function of volume, such that you can plug in and then do the integration directly. Okay? So next time we'll see some numerical examples, and then we'll finish chapter 8 next time.